Hello, everyone. Good afternoon. My name is Akshay Ranchal, and this is a CFD short course on Introduction to Modern CFD being conducted at CHT 21. This talk concerns the background and a brief history of CFD. Here is an outline of the course, this talk, of course, and then the next talk would be on the governing equations. And we'll then move on to the finite volume method and its various aspects. Lecture 6 would concern the pressure projection and the simple method, which is widely used today in most commercial applications. The final two lectures would deal with the turbulent flow and the future trends in CFD. Some comments. Due to limited time available, my focus in this course is going to be on the finite volume method. Other methods such as finite element, lattice-Boltzmann, spectral, etc., can also be very useful for many practical problems. However, we will not go into those details here. Also, with this course, we offer free download of our Answer and CFD Studio shell, which is a complete Navier-Stokes solver with IO and pre-processing and post-processing. It's given to you for 6 months free, and then it's extendable on request for non-commercial purposes. We also provide hands-on training, and please visit our website for those options. What is CFD? Why CFD? And then a brief history and some applications. So what is CFD? Well, the fluids are all around us and fluids are inside us. We are surrounded by air. 2/3 of the Earth's surface is water and 2/3 of the human body is water. So CFD basically predicts the behavior of fluids, plastics, and deforming solids. It is a very challenging profession. And for me, CFD has been fun. And I hope it is for you. Our physical world is roughly divided into solids and fluids. Solids, in the absence of external forces, retain their shape, independence of their location or surroundings. Fluids, on the other hand, flow to conform to their boundaries. Liquids form a visible free surface that may or may not fill a containment volume. Gases completely fill the containment vessels and have no visible surface. There is a special case of a gaseous phase, which is called plasma. It's basically when the molecules of the gas split into atoms and get electronically charged. It's called an ionized gas, usually at very high temperatures. So, as you know, in reality, there are no solids and fluids. There is a continuous transition between solids, liquids, and gaseous phases. Just a question of temperature and pressure to which we subject them to. So there are no solids. Solids are just fluids at rest. Deformable solids are called plastics. So as far as I'm concerned, CFD can span the total range of materials that we encounter. The next question is, why do we do it? Well, simply, to understand our physical and biological world, we need CFD. As I said, we are made of fluids and around us. So every human endeavor involves fluids. So it's better to know and understand the fluids and know what to do with them and how to do it. So that's why we need CFD. What can we do with CFD? Well, CFD applications span human existence, industry, environment, human body, biosphere, you name it. CFD tools are critical to understanding these components of our existence. Take aerospace, where CFD originated. It's dominated by CFD today. No engine is designed actually in the lab anymore. It's designed in a CFD lab. Okay. Energy, transportation, national security, engineering design, food and chemical processing, consumer electronics, environment. CFD is playing a very big role in environment, disaster management, and of course, sustainability. Life sciences, a lot of progress is being made with CFD in life sciences, earth and biological sciences, astronomy and outer space. And CFD is even playing an increasing role in virtual reality, animation, and even in the entertainment film industry. So I'm going to give you a personal perspective of how we came to be and how CFD developed. It's a little bit of a repeat for those who attended my plenary lecture, but I think for those who did not, it will make some sense. I grew up in the remote hills of Himalayas. It was a tiny hamlet of 3 families, 6 adults and 11 children, I remember to this day. I never thought this time-forgotten place will be known throughout the world. You can see on the right-hand side, beautiful surroundings dominated by hills of Himalayas. And there's a little village here that used to be little. Now there are too many houses, but in those days you couldn't see any house at all. There were 3 houses 100 meters apart, starting somewhere here. I never dreamt of participating in the birth of a new branch of engineering science. I thought I was more likely to raise sheep, which was the dominant local profession. But I witnessed the emergence of CFD at Imperial College, and McLeodganj became the home to Dalai Lama and a symbol of rejuvenation of Buddhism, a cause célèbre for human rights, and a prominent place on the political maps of India, China, and the US. So I'm a lucky man at the right place at the right time. As happens often in science, any given development comes after a long series of pioneers who had laid the foundation for that. That's what happened to CFD. It was based upon the work that had been going on for approximately 300 years. During those periods, finite difference method was developed, numerical analysis was put on a sure footing, matrix theory was developed, variational methods were developed by mathematicians. And then, of course, the minimizing principles were developed, such as the Hamiltonian, which basically says that every system seeks its minimum energy. Richardson, Courant, Fredericks, and Levy had made seminal contribution to the theory of numerical methods. And then one very important development that occurred was 1952, when Courant introduced the concept of upwind or one-sided differences, which was to prove very useful in the development of CFD for high-speed flows. Believe it or not, before electronic computers came, CFD was being done. We just didn't call it CFD. Thom in 1953 developed a finite difference solution for flow past a cylinder for a stable solution he was able to achieve for a Reynolds number of 50. He used a stream function vorticity method with central finite differences and an iterative method to solve the matrix. Now, how did he do it? Well, he paid what he calls urchins, which were street children, and he said, for every multiplication, division, and addition, I'll pay you maybe a penny for 100 calculations, or something of that nature. That's how I did it. Southwell developed a very important concept, which is the relaxation. This allows you to speed up the rate of convergence of a matrix with certain properties, which are today called Young's A property. And this is applicable to elliptical problems, which is very prominent in fluid flow. Allen and Southwell used this relaxation to develop the flow past the cylinder up to a Reynolds number 1000 from the 50 that Thom had. They also made another innovation, which was they employed conformal transformation. An infinite domain behind or around the cylinder was mapped into a finite domain through analytical transformation. Tom and Apple, Kawaguchi, Simony, and many others made very notable contributions during this period. But the actual CFD started lockstep with the electronic computer systems. So birth of CFD can be attributed to two brilliant scientists, Frank Harlow at Los Alamos and Brian Spalding at Imperial College. Los Alamos got its first IBM 705 in 1953. And Frank Harlow started working soon thereafter on using it for fluid flow problems. Imperial College saw its IBM 7090 in 1962, and soon thereafter, Brian Spalding at Imperial College started using it for fluid flow problems. Interesting thing is that both worked independently without knowing much about each other's work till it was almost done. These are the days when there was no internet, telephone, you had to go through an operator, and airlines were very expensive for the average person. But of the two, it was Spalding who made CFD a common and popular tool for engineers. Frank Harlow was at a national lab, highly secretive part of the Manhattan Project. That's where the first atomic bomb was developed and exploded. So he was working on defense problems. So his interest was not to commercialize his technology or get it outside. It was perhaps classified and set eyes only. So the computers that heralded CFD at Los Alamos was 701. It was called a defense calculator and was announced to the public on April 29, 1952, and was IBM's first commercial scientific computer. Just to give you an idea for those young people today, the total memory of this system was 2,000 words of 36 bits. So that comes to approximately 9K when expanded to 9 kilobytes when expanded to 4,000 words. Today's laptops would easily have 1 gigabyte of memory, which is a factor of 10 to the 7 from those days. Cycle time was an amazing 12 microseconds. Well, today's fastest computers talk of nanosecond, and the fastest ones run at about 0.19 nanoseconds. So that's a factor of 10 to the 4 or more. So an addition required 60 microseconds and a multiplication division 450 microseconds. You can imagine that's 450 microseconds is almost a millisecond, 1,000 a minute. There are people, they were human beings who could compute, multiply faster than that. Similar calculations today take less than a nanosecond. So today, floating point operation gigaflops are 10 to the 9 are being achieved, and they are very common. And we are breaking through the teraflops barrier, 10 to the 12. So you can compare those. At Imperial College, it was 7090 that arrived in 1962. And actually 1959 was introduced in November of 1959 by 7090 was introduced in November 1959 by IBM. It was a transistorized version of the vacuum tube, which was before that, IBM 709. And of course, 701 was a vacuum tube. A typical system cost $3 million. And though it was much smaller than the original ones, computer of 701 vacuum ones, it still filled a room. The 7090 expanded the memory to 32K words and with 36 bits, so which is about 4.5 bytes. So you're talking about 100K odd bytes. And the basic memory cycle had been reduced by a factor of 6 from 12 to 2.18 microseconds. But one important thing that IBM introduced with 7094, which was the upgraded 7090, was the double precision floating math. Today, double precision is default for most CFD applications, and we are exploring quad precision for tough applications. So how did CFD emerge at Imperial College? Well, it started emerging in 1960s, mid-1960s. But like as I said, happens with science, so it happened with CFD at Imperial College. That Prologue was set by some very important development that Spalding's group had already undertaken. Spalding had developed a common format for fluid flow, heat transfer, and mass transfer over a decade or so. A universal unified theory of boundary layer jets and wake was developed, which combined these three different kind of flows into one and could be considered the first unified theory in fluid dynamics. Before that, we looked at each solution, each aspect of flow or each application as a distinct application. More important than these two, Spalding had done with his students an extensive in-depth survey of experimental data to determine the universal empirical constants that are needed for turbulence. These came very handy when it came to applying CFD to practical problems. He had also done very innovative experimental and theoretical work in combustion. This included the first understanding of how droplets of a fuel burn. He had developed what is now known as the B factor, or the Spalding number for mass transfer application, which simplified the process of computing and dealing with mass transfer. So these would prove very crucial to CFD. So what did people do before CFD? Well, the classical approach to find a solution to the governing equation was to assume a generalized profile for velocity, temperature, or other independent variables. This was known as the similarity profile method. Basically, you said that, let's say velocity we're dealing with, that it's some function of distance from the wall or some distance, such as a polynomial function, a log function, exponential function, anything you think fits the flow that you expect. This profile is then inserted in the governing equations, which yields algebraic equations with empirical constants, which are essentially the coefficients of the profile you assume. So these constants are then derived from satisfying the boundary and initial conditions. Okay, so you have to have the right number of coefficients and the right number of boundary initial conditions. Or if there are too many coefficients, then the method was to go to what they call the moments method, where you develop the first or second or third moment of one of the equations and use that. Von Karman and Polhausen were the early proponents of this profile method, or the similarity profile method. So the classical turbulent profile, for example, for walls, was a three-part log linear profile with viscous, transitional, and fully turbulent layers. Viscous part was linear, turbulent part was log, and there was a transition between the two. The other option for turbulent flows, simple wall flows and pipes, was the so-called 1/7 power law, which worked for a range of Reynolds numbers. So what Spalding concluded, that the optimum profile can be utilized for such flows by representing it as a piecewise polynomial rather than a single analytic function. Take, for example, a parabola. Well, if you go into small enough sections, you can represent that parabola as a piecewise linear function, okay? There'll be some approximation, but nonetheless, it'll be a fairly good representation. So it freed one from the tyranny of having to find an ideal profile. Now, I didn't look for which profile fits my flow. I say, well, it's a piecewise profile. I just have to figure out how many pieces I need. So there is a parallel between piecewise profile and the finite difference approach, but there is a difference that though both lead to algebraic equations, the profile method leads to a number of arbitrary constants that have to be matched to the initial and boundary conditions. We don't do that in CFD. The boundary condition, initial conditions automatically come into the play through the boundaries or initial setup. So Patankar, who had joined in '64, worked with Spalding and developed a general what was called integral profile boundary layer code. So the nice thing was that it worked for any boundary layer type of flow. It worked for walls, wall jets, it worked for walls, it worked for pipes, it worked for jets. Nonetheless, the big drawback was that this method worked only for simple boundary layers when there was a boundary layer. It could not be made to work for many practical flows, not yet, not at that time. Many practical flows have separation, high streamline, curvature, or high pressure gradients. These are called elliptic flows rather than the parabolic flows with the boundary layer flows. So Spalding needed his unified theory to work for such flows also. Okay, so Mika Wolfstein had joined in October 1964. So Spalding said, why don't you take the unified theory and make it work for the impinging jet? Okay, and I joined in September 1965. So the Brian said, well, Mika is doing for impinging jet. Why don't we take another class of flows, the ones with separation? And he selected two, backward flow behind a step and driven lid square cavity as the examples for separated flow. And he said, well, you solve these two. So had we been successful, these two extensions would have firmly established unified theory for both parabolic and elliptic flows. But that was not to be. Neither Wolfstein nor I were able to make any headway. We tried all kind of profile, all kind of options, and played around with it. We could not get converged or decent solutions for our flows. We began to suspect that it wasn't we, that there was something wrong with the unified theory. We also realized, and we knew that boundary layer is destroyed by strong pressure gradient or geometry-induced separation. So something was going on that we didn't understand. Spalding realized then that the axial diffusion terms that are important in elliptic flows, they're ignored in parabolic flows. It is those terms that are leading to separation and high streamline curvature. That convection is becoming dominant in many situations, and diffusion is becoming dominant in the high streamline curvature and separation flow, which was not accounted for the piecewise profile of a single variable. We'll have to extend the piecewise profile method to add additional profiles. So that was not a job that seemed worth doing. So Spalding said, do something else. So we looked in the literature, and both Wolfstein and I independently came to the conclusion that finite difference method was perhaps the most general and optimum method for our situations. It's simpler and more general than piecewise profile with its many coefficients. So we used it, and we were very successful in solving our problem. Wolfstein solved his wall jet problem. I solved my boundary backward facing step and driven cavity problems. After subsequent meeting, Brian got me and Wolfstein together, and we realized that we were essentially using the same approach. Our problems were different. We also realized that we were both facing the same high numerical instability for high Reynolds number flows. As we ramped up the flow, we'll run into numerical instability. So in looking at the causes of this instability, we realized that it was dependent upon the Peclet number. If the local Peclet number exceeded 2, the matrix was no longer positive definite. Now, positive definite matrix is a must for iterative solvers. Because our problems were too big for direct solvers, we had to use iterative solvers. So for Peclet number of 2, the influence of convective term exceeds that of diffusion and makes the matrix non-positive definite. So this led Brian to propose the upwind concept. And the wind from the north always brings cold, at least in northern hemisphere. And Spalding had lived downstream a pig farm. He says it always stinks when I'm downwind from the pig farm. As again happens very often, We realized later that Courant had already proposed the Upwind scheme more than a decade earlier in 1952. Quite often it happens in science. If you have a good original idea, believe me, somebody else has already worked on it. The other key concept that led to the Imperial College of Finite Volume approach was this one. Spalding made a very important physical analogy. He said finite difference grid is nothing but a bunch of volumes connected by a bunch of grid lines. Now the volumes are the tanks and the grid lines are the tubes. He said we can think of it those ways. So look at this element here, which is called P. It's connected by 4 tubes to east, west, north, and south, and flow can only go in this direction through these tubes. And the balance is maintained by these 5 elements together. So what this did was the tank and tube, it changed our thinking. We started thinking in terms of volumes and not in terms of differences, finite differences. We started talking in terms of fluxes and not gradients. So physics became the predominant mode of figuring out what to do. We didn't require Taylor series, which also means the Taylor series equate order with accuracy. In a Taylor series, a 4th order scheme is more accurate than 2nd order scheme. Well, in theory, that is true. In practice, that doesn't work. Quite often, a 4th order scheme either doesn't work or is no more accurate, or perhaps even maybe less accurate. For example, for a supersonic flow, a 2nd order scheme will only not be less accurate than 1st order, but it will even lead to disastrous results. So Micha Wolfstein and I started assembling a general Navier-Stokes solver based upon stream function vorticity variables that will work for any 2D flow. We didn't realize at that time, but this was the formalization of the finite volume method. The first paper started appearing soon thereafter. Our first paper came in 1966. Then there was one in 67, 69, 69. So over a period of 3 years, we had 4 or 5 papers that established the finite volume method. These concepts were later refined as time went on. In 68, we started becoming wise to the numerical diffusion or false diffusion due to Upwind scheme. Upwind scheme allows you to compute any Reynolds number flow, but it introduces a false diffusion, essentially lowering the effective Reynolds number. So Wolfstein published one of the first papers on false diffusion, which showed that the amount of numerical diffusion or false diffusion depends on both the speed of the flow and the angle of the flow line to the grid line. To counter this effect, the false diffusion, Spalding proposed an exponential method where we instead of using a linear exponential or a polynomial profile, we'll use the exponential profile for finite differences if we're using a Taylor series. So that proved to be very expensive. And I was working on a hybrid scheme where there was an automatic blending based upon the local Peclet number. The problem was Peclet number of 2. So I developed a scheme where if Peclet number is less than 2, central differences scheme we used. If Peclet number is more than 2, Upwind scheme we use. So every point, it dynamically checks the Peclet number and uses the right scheme. So this later became the standard. And of course, now there are many other options based more or less upon the same idea that you have to have an automatic blending scheme to effectively allow for convection. Second thing that happened, another refinement of the concept came when I became fascinated with the Gauss theorem and the integral approach to Navier-Stokes equations. There was a classical fight in the centuries ago, 2 centuries ago, between the differential approach of Newton and the integral approach of Leibniz. So basically, Micha and I had a lot of discussions on which one is better. The same set of algebraic equation can be derived from both. Okay. Wolfstein eventually went on to write his thesis on the basis of Taylor series, and I decided to submit mine based upon the integral approach and the formal control volume integration with Gauss theorem. So this was the first thesis in CFD that I'm aware of, which used integral approach or finite Gauss theorem approach. Though each has its usefulness, the finite Gauss theorem more easily leads to formal finite volume method for arbitrary boundaries and is more or less the standard procedure for deriving finite volume equations, much simpler and much more general. So by the start of 1969, Spalding had realized the potential of CFD. He arranged a post-experience course at Imperial College, which was attended by a large number of academic and industrial experts from UK and abroad. Our first book on CFD, Heat and Mass Transfer Recirculating Flow, which was actually the first book on CFD, was published by Academic Press. I'm often questioned about, asked by people about the order of the authors. Spalding had a very strict rule that all publications carry names in alphabetic order. Both myself and Wolfstein had academic positions abroad, so we're going abroad. Spalding asked David Gosman, who had just completed his thesis on experimental work, to compile and edit the contribution from myself, Spalding, and Wolfstein, and put them into one place along with the code, which was taken over by Sam Poon from me and Micha Wolfstein. So the first general purpose CFD code answer also became available in 1969. It was freely distributed, it was in the book, and it was available on demand to anybody who wrote to us. In those days, there was no concern for intellectual property and no lawyers asking us questions. So you wanted a code, you write to us, we send it to you. Another development was the first commercial services in CFD became available in 1969. Spalding incorporated CHAM, Combustion, Heat and Mass Transfer Limited. So as far as I'm concerned, CFD was ushered in as an analysis tool for practicing engineers in 1969. Of course, till this time, the focus had been on two-dimensional flows. Around 1970, Brian became convinced that stream function vorticity approach was not viable for three-dimensional flows. He played around with it for 3-4 years and couldn't get an effective solution. So he abandoned it and turned to primitive variables, velocity and pressure. Harlow had already introduced the concept of staggered grade and primitive variables, as well as a decoupled pressure for transient multidimensional flow. Cholesky had pointed out in 1967 that any scalar can be used in lieu of pressure, giving birth to the strategy of pressure decoupling, which is the popular method today for solving certainly the incompressible flow problems. This is based on the fact that any vector, such as velocity, can be decomposed into rotational part, which is responsible for vorticity, and the irrotational part, which is represented by pressure. These can be linearly added to get the total velocity component like any vector. So Potanker and Spalding in 1972 borrowed these ideas and they combined these into a method called Simple. This revolutionized CFD practice, and most commercial codes today employ some variation of Simple at least one of its options. Now, one caution I have here is that the Simple approach works well only for subsonic flow. You can make it work for higher speed flows, but it's like trying to reach backward to catch your nose. For high Mach number flows, a density-based approach is a better approach and is preferred today. Now, to make CFD practical, other thing we needed was turbulence, handling the turbulence or turbulence models. So he was one of the first to see the potential of CFD. So he knew that CFD would not be really useful unless it dealt with turbulence and combustion. Both play a very prominent role in engineering practice. The standard model for turbulence in those days was the Prandtl's mixing length model. Okay, but it worked only for simple boundary layers, jets, and wakes. Most practical flows do not fit in this category. For example, mixing length model could not predict the heat or mass transfer in recirculating flows at all. The heat transfer is maximized at the point of reattachment, whereas shear is zero. So there's no equivalence between the two. So based on the work of Kolmogorov, Prandtl, Chow, and Rota, Spalding had derived a number of options for turbulence models. This was the one equation model based on turbulence kinetic energy, then two equations models based upon kinetic energy and length scale, kinetic energy and vorticity, kinetic energy and dissipation. So working with students, he had already obtained universal constants. So he developed a number of these codes and tried all of them. And there are a number of theses from that time for Imperial College with all these options. Harlow and his co-workers had published a paper on K-epsilon model. So around 1972, Lauder and Spalding adopted that as the preferable tool and settled down on the K-epsilon model. So both Imperial College and Los Alamos groups basically came in sync, and this established turbulence modeling as a practical tool. Today, of course, another model in turbulence that has gained prominence is K omega model. And then, of course, there are many other models such as LES, DNS, and all that. So we're still working on it. It's still something we're working on. The other important thing was combustion. Combustion plays a very important role in energy generation transformation. It's almost 80% of energy today is generated by combustion one way or other. Spalding had worked on combustion since 1940s, so he understood it very well. He knew that turbulence intermittency plays a very strong role in combustion. Two reactants have to be present at the same location at the same time to react. Rand's equation gives you the time average value. It doesn't tell you the full story, that there may be average value, but the two things may not be present at the same time at the same time. Not that different from a marriage where you have to have two reactants present at the same time to have a product. So Spalding published a paper that introduced the eddy breakup concept for turbulence reaction rate. This was the first formal multi-fluid model. Fluid was divided into mixed and unmixed and burnt and unburnt. The result was a rate expression that put the upper limit on the chemical reaction that can occur due to turbulence intermittency. This and further refinement of this idea, including many multi-fluid models such as laminar flame nets, led to a revolution in modeling of flows with combustion. Finite element method is very prominent also in fluid dynamics today. Two of the pioneers in this field were Johann Argyris, who was at Imperial College at that time, same time. And then there was Zinkiewicz, who was at Swansea, not very far away, far from London. We were in touch with both of them. We had a lot of discussions, and it was a hot topic of discussion between them as to which one was a better method. Finite element was initially developed for structural applications. It was based upon a minimization Hamiltonian, and it worked for that reason that you could seek the minimum energy of a system. In early days, finite element was unsuitable for high Reynolds number flows. There was no clear theoretical basis because Hamiltonian doesn't exist for nonlinear systems. So the other problem with finite element was that it uses global error minimization. You don't ensure that each control volume has a minimum, or each node or each element has a minimum threshold. You only assure that the overall global error is minimized. That may mean at some points the error may be high, at some points low. You're seeing the total average. So for highly nonlinear system, local mass balance can be very critical. For example, in combustion, a small change in temperature can lead to a fourth order change in reaction rate. So we stuck with finite volumes. Over the years, both have borrowed from each other. And today, the differences are more semantics than substance. You can do anything with either of those. Nonetheless, primarily because of the error minimization and the convenience for nonlinear system, the commercial codes mostly use finite volume. Even today, though finite elements are beginning to make some headway as the computers are becoming faster and you can go to faster tolerance on errors. So a bit of nostalgia and synopsis before I go on to other things. One interesting fact is that CFD name was not coined by Harlow or Spalding. It was first used by Pat Roche in his famous book, which is called Computational Fluid Dynamics. The CFD was in a heyday at Imperial College between 65 and 75. It was the largest CFD group, about 40 researchers. They were working on it. Even today, I doubt there is a larger group under a single person. It was a very productive period, and we had weekly seminars. Okay, with 40 students and faculty, almost everybody's turn came a year later. Spalding also had two brilliant faculty members. Jim Whitelaw worked on experiments and Brian Launder on turbulence. This gave a synergy to all of them, so we could test our turbulence models in the CFD, and experimental work could be used to verify CFD and like that, so it was a good synergy. So this approach led to CFD as an engineering tool, and it unified the flow, heat, and mass transport, and the focus turned to physics rather than mathematics, which is very important for engineers. We're concerned with engineering practice. If we didn't understand all the theoretical aspects, but knew enough to get the job done, we did it. Proof of the pudding is in eating it. That's what we believe. Turbulence is a good example. We don't fully understand it even today, but we use the best information and the best models available and produce something that engineers could use for design purposes. Many of today's commercial codes, which are well known, trace their origin to the work at Imperial College. Answer, our code, CFX, CFDAs, Fluent, OpenFOAM, Star CD, they are all based upon the work done then. All of them, one way or another, got the codes that were developed by Imperial College. Let's look at a few applications before we finish. Here is the case of a tsunami, imagine tsunami coming and hitting the coast of Cannes, sorry. And this is the actual coastline of Cannes. And you can see in this one how the tsunami inundates part of the shore, and some lower floors of the buildings get inundated with water, and also the whole area that gets inundated with water. Okay, you see a little far there, you see on the far right there, you'll see the water coming and inundating the whole area of that island. Okay. So this proves very useful for disaster management. This is a different example that in sustainability, wind turbines are today form what you call the wind farms to generate energy from alternate sources, in this case, wind. It's very important to understand the flow in and around those turbines, behind those turbines, so you know how to place them in a large farm, so the energy generation is maximized. So one doesn't go into the wake of the other and generate nothing, okay? So for that reason, it's very important to place them at a certain distance from each other, and what is that optimum distance so we can generate the maximum energy. This is an example from the diffusion of a drug into a brain, because blood-brain barrier is a very important concept, barrier, and many drugs do not cross this barrier. Okay, so for some reasons, for let's say tumors in the brain, it may be better to inject directly into the brain. Then the question is, how fast does the drug diffuse? Where does it go? What the concentrations are? And these are all done by CFD today. Let's look at the propagation of a virus, a very topical project. Okay, here is a person who's coughing 3 times with a 1 second gap. And you can see the person on the left is coughing and the right is the recipient. Now you can see that the flow plays a big role. it's not just 6 feet apart. It's a question of what the ventilation is, okay? If you are downwind of somebody, like this recipient is in the downflow situation, you're going to be inundated and immersed in the virus particles. If, on the other hand, the ventilation is such that that you are not directly in the path, you may have some time to escape. Or if you're completely down upwind, you will get nothing. So I think the wise thing here is to not just look at the distance, but also look at how the wind is blowing. Are you downwind of a person or upwind, and stay away in areas where you are potentially upwind of any source. So here is my final slide for a successful engineer. Basically, you can if you think you can. Okay, Virgil said that in Latin. I won't try to read it, but what it says is they can because they think they can. Now, Spalding made an important contribution. He said, let's look at the inverse of that. You can if you don't think you can't. Like if you know you can't climb a mountain, you're not going to try and climb it. But if you're not sure, then you don't know if you can or cannot climb a mountain. So in that case, it's worth a try, right? So it's very important to think that if I know I can't, then not attempt it. And if I don't know if I can't, then give it a shot. So make use of what you know and what you have to do a job that must be done to the best of your knowledge. You don't have the perfect turbulence model. Use the best information about turbulence for that specific application that you have in mind, okay? The other important advice I have for young people is don't worry about what other people say or do. What do you care what other people think? Read that book from Feynman. He was my hero. And I think that he's on the right track when he says, don't care about what others think. So the real test is, can you accomplish what others say can't be done? CFD is challenging. For me, CFD has been fun. Thank you very much. Any questions? We can go to that. And thank you for your time. Bye.